Hi, today I'm talking about LeetCode problem 1226, the Dining Philosophers. And I had to actually read this problem a few times to be sure that I understood it. It's a very un-LeetCode-like problem. But once I did understand it, I really liked this problem. I thought it was very interesting. So let me explain it to you using this diagram. Basically, we've got 5 philosophers sitting at a table. I've labeled them here 0 through 4. And at this table, there are 5 forks, 0 through 4, also labeled in green. So the philosophers need to hold 2 forks in their hands to eat their spaghetti. If they try to eat the spaghetti without 2 forks, then they won't be able to. And yeah, they can pick up the forks and they can put the forks down and they can eat spaghetti. So the problem is that all of these philosophers are going to try to simultaneously eat their spaghetti. And what we want to do is organize it so that they can eat as much spaghetti as they want, meaning have as many periods where they pick up their forks and eat spaghetti and put their forks back down, as many of those periods as we want, without ever getting into the problem of one philosopher or of the philosophers trying to fight for the same fork. So you can imagine just, you have, if you were to just tell your philosophers, hey, grab your right fork and your left fork and then just eat and then put your forks down when you're done. The problem is that 0 and 1 would both be trying to grab the same fork. And 1 is trying to grab the same fork that 2 is. The philosophers need 2 forks in order to eat. And there are only 5 forks. Like there's the same number of forks as there are philosophers. So this problem is asking you to write or to create an object that will manage 5 threads. Each thread is acting on behalf of one of the philosophers. So there's a thread for philosopher 0, and it's going to try to pick up the forks and eat spaghetti. There's a thread for philosopher 1 that wants to do the same thing, and so on. And what you need to do is manage these philosophers so that they can all pick up their forks and successfully eat their spaghetti. And the problem is going to give you a number n, which means the number of, I think of it as plates of spaghetti that the philosophers are going to eat. So if you're a philosopher, you can pick up your 2 forks, you can eat 1 plate of spaghetti. You could hold on to the forks and just keep eating your plates of spaghetti. But then the other philosophers wouldn't get to eat theirs. So you've got to somehow manage across multiple threads the coordination so that all your philosophers can eat at the same time. So my first solution to this wound up being pretty slow, but I went with the approach of slow and steady wins the race. One thing that is maybe not quite so good about this problem is that there's basically one good way to solve it. So if you look at the accepted solutions, pretty much everyone is in the same distribution. Almost everyone solves it in about the same time, except for me, I've invented a slower way to solve the problem than most everybody else did. But then after thinking about it a little bit more, I figured out the faster way. So let me talk to you about the slower way first. And basically what we're going to use to solve this is what is called a lock in Python. So a lock is just this object which has, a lock, it has state, like is it locked? It's called something else, but like there's just a state, locked, which is basically just a Boolean, true or false. It's conveying whether the lock has been locked or not. There's also acquire, and what acquire does, it's a function that when you call it, it's going to try to lock the lock. And if the lock is unlocked, then it will just lock the lock and return back to the caller. If the lock is locked, then what acquire is going to do by default is it's going to block. And block means the execution of the thread is not going to continue until acquire stops blocking and returns back. So somebody, a caller calls acquire. If the lock is unlocked, it just immediately returns. It immediately locks the lock and then returns, and the caller can go on its way. If caller calls acquire and the lock is already locked, then it's just going to wait. Like this function call will take as long as it takes for the lock to become unlocked and then return back to the caller. And so then the caller can return on its way, or can continue on its way. And then the final function here is just called release. And release just flips the state from locked to unlocked. So basically, locks, pretty simple, but they're how you can coordinate shared resources across multiple threads. And that's exactly what we need to do for this problem. So we want to make sure that our philosophers can all share their forks across the different threads. And the way we're going to do that, well, the easiest, the slow but easy solution is we can realize that, well, if just one philosopher was eating at a time, then we would never run into any contention. That is, there would never be any problems. Nobody's fighting for the same forks. So if we just say, hey, philosopher 0, you can start, you pick up both of your forks, eat your plate of spaghetti, set your forks down, and then it goes on to the next philosopher. Philosopher 1, philosopher 2, philosopher 3. So you can kind of right away see, like, not only is this going, and it's just going to loop. So if we need to eat 20 plates of spaghetti, we're just going to loop 20 times. However many times, we're just going to keep looping. You can kind of see, one, how this is obviously going to work, because it's impossible for us to contend if only one guy is eating at a time. And then two, you can see how it's going to be slower than everybody else's solution. And the reason is, of course, we have 5 forks and 5 philosophers, and it takes 2 forks to eat a meal. Well, the maximum kind of throughput that we can do is 2 philosophers simultaneously eating. We can never do more than that because there aren't enough forks to do anymore. But doing less than that just means we're going to be slower. So my solution has just 1 philosopher eating at a time, but that means we're basically going at half the speed that we might be going. Half the speed because instead of 2 people eating at once, there's just 1 guy eating at once. So let me show you what that code looks like. I think it's pretty straightforward. My solution object is going to have as its initialization function. So what I'm going to do when I start is I'm going to create a lock object, and we get the locks from the threading module. I'm going to create a lock object, and basically I want there to be 1 lock per philosopher. And the locks are just going to represent, like, hey, it's your turn to eat. So the philosophers are going to try to acquire their lock. Let me talk more about that in a second. So, okay, we create a lock, 1 for each of the philosophers. And then what I'm going to do is lock all of the philosophers but the philosopher in the 0 position. So in my initialization, I just go 1 to 5 to acquire, or rather to lock all of the locks except for lock 0. Okay? And so then this function is what the LeetCode problem wants me to write, wants to eat. And this function is going to be called by the 5 threads that represent the 5 philosophers. So this function gets called 5 times simultaneously. And what I'm doing here in line 23 is I'm figuring out who the next philosopher is. This is the philosopher who are going to say, okay, I'm done eating, you can go. And that philosopher, the philosopher input is just like the number of the philosopher you are. So 0, 1, 2, 3, etc. So the next philosopher is just philosopher plus 1 mod 5. So that when we're at philosopher 4, plus 1, 5, mod 5, 0. So we just kind of loop like that. So that's the next philosopher. What I'm going to do is I'm going to try to acquire the lock. So remember, this is getting called 5 times simultaneously by my 5 philosophers. Philosopher 0, his lock is unlocked. I didn't lock it up here. So philosopher 0's lock is unlocked, and he's just going to continue on right away. He acquires his lock, and acquire just locks his lock, and then returns execution back to him. So what he does is he picks up his left fork, picks up his right fork, eats, puts his fork down, and then the next philosopher, he unlocks that philosopher's lock. So that's what happens for philosopher 0. And remember, he never unlocked his own lock. And that's important because if in is greater than 1, that means our 5 threads are going to call wants to eat in times. So there are 5 executions of this of this function if in is equal to 1. If in is equal to 2, there are 10 executions of it, 3, 15, and so on. Okay, so philosopher 0, we just walked through how he worked. Philosopher 1, what he's going to do, his next philosopher, of course, is 2. Philosopher 1 plus 1 is 2. Mod 5 is 2. He's going to try to acquire his lock. But remember, that's going to fail because I locked it in line 9. I locked everybody but 0 in line 9. So rather, I shouldn't say it's going to fail. It's going to block. He tries to acquire his lock, and you can think of it as this is just going to take forever. He's not getting it back because it blocks. So like this is a function that's going to take forever. Or when I say forever, what I really mean is it's going to take until philosopher 0 has finished execution up to line 31, and then philosopher 0 picks philosopher 0's next philosopher, which is 1, and philosopher 0, when executing this function, releases philosopher 1's lock. And so then philosopher 1 moves past line 25, and philosopher 1 picks up his left fork, right fork, eats, left fork, right fork, and philosopher 1 releases philosopher 2. And then that just goes on a loop forever, basically. Philosopher 0 eats, unlocks philosopher 1. Philosopher 1 locks his lock again, picks up his forks, eats, puts his forks back down. Philosopher 1 unlocks 2 without unlocking himself. And so you can think like, okay, if n is greater than 2, or if n is greater than 1, like we have multiple plates of spaghetti, philosophers 0 and 1 are back at this line trying to acquire their locks again. But remember, when they acquire their locks, they lock it, and they never release their own lock. You only release the lock of the philosopher next to you. And so then that just enables, this progression where you circle around eating. So I think the advantage of this solution is that it's really simple, and you can tell it's going to work for sure, because there's no contention. There's no possible way to contend. One problem with locks is the idea of deadlocks. So what I was saying with acquire a second ago, you can imagine if 2 philosophers try to acquire a locked lock, it's never going to return for them. Or if nobody is going to release your lock, you're just going to wait forever. Or if I'm waiting on, if philosopher 1 is waiting on philosopher 2 to unlock something, and philosopher 2 is waiting on philosopher 3 to unlock something, and philosopher 3 is waiting on philosopher 1 to unlock something, you can just create this kind of deadlock where everybody's waiting on someone else, and so nothing ever gets unlocked. And my solution of just letting one philosopher eat at a time means that this can't happen. So it's simple, but of course it's slow. And so then having solved it, the first time I submitted it, I think I got 6 percentile for speed. So then I thought a bit more about what I was doing and how I could, solve it kind of the correct way. And when I say correct way, I mean the way that it's optimal to solve. So let's always get 2 philosophers eating at the same time. And making that change, I got up to 91.5 percentile for speed, but I'm pretty sure this is just a lot of, it's also random variation in here. So I think probably all solutions, other than the first one I showed you, all solutions that involve 2 philosophers simultaneously eating are going to effectively be about the same speed. But let me just walk through this 2 philosophers eating simultaneously. So for this for this idea, what we have to do, we have to figure out how can we grab forks without ever getting into the deadlock scenario. So we can't say like, hey, everybody just grab your left fork. Let me erase all this stuff. I don't know why I made arrows to these guys. We can't say everybody just grab your left fork. Or when I think about it, I think of grabbing the fork that matches your index. So 0 philosopher grabs 0, 1 grabs 1, 2 is going to grab 2, 3 is going to grab 3, 4 is going to grab 4. The problem with this is they all succeed and they all grab their forks. And so if we want to grab the next fork, like now everyone is going to have contention. So like nobody is going to eat. Nobody's going to eat. Nobody's going to give up a fork. Or if they do, they're all going to give up the wrong fork. So, or they're just going to, pass forks back and forth. So because the philosophers have an index, what I decided was that the even-numbered philosophers would grab their fork, meaning the fork that matches their index, and the odd-numbered philosophers would grab the next philosopher's fork, meaning the fork that matches the index of the next philosopher. So 0 grabs 0, 1 grabs 1, 2 is going to try to grab 2, 3 is going to try to grab 4, that's the next philosopher, 4 is going to try to grab 4. So like what this is doing is it's guaranteeing that there is multiple people trying to get the same forks. And I should add that basically I have a lock for each of the forks. So when I say they're trying to grab a fork, what I mean is they're trying to acquire the lock that corresponds to that fork. So we know 0 is going to succeed. He's going to grab his fork. And then he's going to, well, two things might happen. One possibility is that 1 succeeds and grabs fork number 2, in which case philosopher 2 is going to be left hanging, waiting to acquire the lock. And then 1 is going to try to grab fork number 1, assuming he got 2. Now, simultaneously, philosopher 0 is going to be trying to grab it. So one of them is going to grab the fork, and the other is going to be blocked. But whoever grabs the fork is going to have 2 forks, which means they're going to eat their plate of spaghetti, and then they're going to put their forks back down and release their locks. So if 1 grabs it first, he's going to eat his spaghetti, release his locks. If 0 grabs it first, he's going to eat his spaghetti, release his locks, and then 1 is going to get unblocked, pick up the fork, and eat it. And that kind of logic is going to apply everywhere. So basically we're just making sure that whoever wins one fork will be able to grab the next fork. And that by coordinating that even-numbered philosophers grab a different kind of fork than odd-numbered philosophers, we're making sure that we never get into the pattern of everyone kind of doing exactly the same thing, which results in no food getting eaten, because nobody can like overcome the contention to get both forks and eat a plate of spaghetti. And what it's going to result in is that like our maximum throughput will get 2 philosophers eating at the same time, so that so that we can complete the task faster. So here I'm not locking any locks at the beginning. And now I'm thinking of the locks not as mapping to philosophers, but as mapping to the forks 0 through 5, or 0 through 4. And none of them are locked at the start. So what we do is we figure out who your next philosopher is, and we know who your philosopher is. And I'm just referring to these labels for forks. So the 0 philosopher's fork is 0. The next philosopher's fork is 1. The first thing we're going to do is try to lock up both forks. So we're going to use like this little bit of math is just handling the evens and odds case. So we're going to add onto the philosopher's number 0 if it's even. So philosopher mod 2 will add 0 if it's even, and we'll add 1 if it's odd. And likewise, in the next line in 22, we're doing the same thing plus 1. So even philosophers try to grab their fork first, and then in the next line, they try to grab the next fork. Odd philosophers try to grab next fork first, then in the next line, they try to grab their fork. And when I say grab, I mean acquire the lock. And then, then they just follow the same sequence of picking up their forks, eating, putting their forks back down, and then releasing their locks, the same locks they grabbed. So yeah, I mean, maybe this is a little simpler, but you can imagine, I mean, maybe it's a little harder to imagine how execution simultaneously happens with 5 threads. But basically, some philosophers will get by two philosophers will get by lines 21 and 22 without blocking. And then they'll eat their meal and they'll release their locks. And then the next philosophers will acquire the locks and they'll eat. So yeah, that's pretty much it. For test cases, what I did for this, in their example, they show you can have, in their constraints, they show that n can be between 1 and 60. So if you have very small constraints like this, and n has to be an integer, it's between 1 and 60, obviously the right thing to do is just to test all numbers between 1 and 60. Because then you can be certain that you are that you have produced the right thing before you submit it. I think if I submit it again, I expect the time will vary. I don't think 90 percentile for speed is going to be very consistent. So yeah, so we're a bit slower. I think it's just going to be a little random depending on how the LeetCode servers are running. But when I ran it, with the old version, 1 philosopher at a time, I think it was definitely slower. I was getting like 6 percentile speed, 20 percentile speed, and now I'm getting 80, 90, 60. I think this is the solution that most people must have. So everyone's speed is going to be kind of similar. But yeah, if you like this video, let me know by clicking the like button. If you want to see more LeetCode problems solved and kind of walked through like this, you should subscribe. Thanks for your time. Bye-bye.